Welcome. Today we're looking into limits of a function. Let's define this. The limits of a function, let's say f of x, is simply the behavior of that function near a particular input. Let's say x naught. Let me show you this. Let's say we have a function f of x is equal to 1 over x. This function, how does it behave if x approaches 0? Yes. What's the behavior if x approaches 0? When I say approaches 0, what do I mean? It means when we put a value here that is not 0, I didn't say x is equal to 0, no. x is approaching 0, something close to 0. What do you think is close to 0? A number. 1, yeah. 1 is close to 0, yes. 1 is close to 0. But I need something closer, something more close. 0.1. What happens? Let's say we have f of x. Let's say we have x values. We have here f of x. If x is close to 0, we can use 0.1 as our x value. Now let's see how the function behaves. What is 1 divided by 0.1? If I place x as 0.1, what is 1 over 0.1? 10. I will stop here. For me to know the actual behavior of this function, I have to go more near. I'll approach closer to 0. So which number is more close to 0 than 0.1? To go closer to 0, I can put 0.01. So if I place x as 0.01, what will happen? We'll have 1 divided by 0.01. When you punch calculator, you will see is 100. If you still want to know the behavior further, you feel like studying further the behavior of this function, what do? We find a number again that is more closer to 0 than 0.01, which should be 0.001. Now place this value as s here and divide. You will have 1000. At this point, you'll be seeing the behavior of this function. As you are trying to go close to 0, the function is going large from 10 to 100 to 1000. The more you go closer, the more the function enlarges. So I can say that the limit as x tends to 0 of f of x is equal to, going larger means it's going to infinity. The behavior of this function is that the function is approaching infinity. The behavior of a function close to a particular input. Now, I want us to know more things about the limit of the function. Yeah. Now, I want you to know that for a limit to exist, we have three conditions that will make a limit to exist. First, the left hand limit must exist. Must exist. Yes, the limit as S goes to a particular input from the left of f of x. This must exist. Also, that's 1. 2, the limit as S goes to an input from the right of f of x must also exist. Yeah. 2 conditions. The left hand limit must exist, right hand limit must exist. The final condition, the third one, is that the left hand limit must be equal to the right hand limit. 3. Limit as S goes to x naught from the left of f of x must be equal to the limit as x goes to x naught from the right of f of x. Negative shows left hand limit. Positive shows right hand limit. So far, this thing is kind of confusing to you. But some of you will see it in your exams, your OBJ exam. Everything is not solving sound. At times, they'll give you questions like GST questions like this. So now, let's practicalize this. Let me show you practical approach to what I'm saying. Okay, we have 2 questions on the board. Solve. The first one says, limit as s approaches 0 from the left of 1 over x. So far, we have solved something like this previously in our example that I've cleaned. Now, I want you to observe something. S here was strictly requested to approach 0 from the left. How do we do that? In this case, we are going to put numbers very close to 0, but less than 0. Left means they are less than your input. So numbers close to 0 and less than 0 is something like, once you are less than 0, you are negative. It's something like 0.1 negative, 0 minus 0.01 minus 0.001. So in this case, if I impute these things, if I want to approach close to 0 from the left, what happens? I will have here my function will be going larger and larger. 1 over this will give us negative 10. 1 over this will give us negative 100. 1 over this will give us negative 1000. So the more I go close to x from the left, the more the behavior of the function is going large. It diverges up to negative infinity. Yes. Let's analyze this one. Question 2. Let's analyze. You know, here says approach 0 from the left. How do we achieve this? We are putting numbers close to 0 at the same time less than 0. So what do? Same thing we did here. But this time, we are checking the behavior of this function. When I put something negative, here I have the right to insert the values of x as negative 0.1, negative 0.01, negative 0.001, if I'm going close to 0, negative 0.0001. These values are what I am expected to put here as numbers close to 0 from the left. If I do that, what happens? I will have it to be 1 over this all squared. And anything you get here, once it is squared, anything negative, once it is squared, becomes positive. And any number between 0 and 1, when you square it, the number becomes smaller. So 1 divided by this gives us something small, which is 1 over 0.01, which is 100. So if I put the second one here as my input, I'll have 1 over negative 0.01 all squared, which is 1 over 0.001. Which is 10,000. In fact, there's no need in these calculations. Once you can decipher the behavior of this function as it goes close to 0 from the left, that's the question. So the behavior of this function as it goes close to 0 from the left is equal to infinity. That is positive. Because the minus was squared, it turned out to become a divergent positive. Yes. Also, this same function, let's assume, is going to the right. The same answer. We'll have it to be positive infinity if it was going to the right. The negative sign have no effect, as you can see. So if it goes to the right, the same answer. Does this mean the limit exists? No. For a limit to actually exist, the value must be real. It must have a finite value, a real finite value. I will explain this in more of the further examples I will give. Let's take more examples. Quickly, let's evaluate the following limits. This is very simple to handle. It's not about solving, it's about understanding what we are dealing with. Actually, the value of x is not 2. X is only approaching 2. So we shall investigate the behavior of the function. How does this behave close to 2? First, let's check the behavior as x approaches 2 from the left. Let's see what happens. For 2x plus 1, let's see what happens when x goes to 2 from the left. So if we are approaching 2 from the left, it means the numbers that will go in as x must be close to 2 and also less than 2. Yes. Which number is close to 2 and less than 2? 1.9. 1.9 is close to 2 and less than 2. If I say go more closer, what will it be? 1.99. Go more closer to 2 from the left than 1.99, what will it be? We have 1.999. Now let's see the behavior of this function from the left. What will be 2 if 1.9 should go in as x? We'll have 2 times 1.9, 3.8 plus 1. We'll have 4.8. Here will give us 4.8. Yeah. These are our s values. S values, yes. And here's our function f of x. How about here? What happens here? When s goes in as 1.99, what do we have? We'll have 2 times 1.99, 3.98, plus 1, 4.98. When x goes in as 1.999, what happens? We'll have 2 times 1.999 plus 1, and that is 4.998. You see, as the function is going close to 2 from the left, the behavior of the function is that the function is approaching a particular number, 5. To approximate this is going close to 5. So the limit as x close to 2 from the left is equal to 5. I am trying to make a point here. Yes, I know it in your head that, yes, I know it, Obina, yes, I know. In your head, you just feel like going straight ahead to plug x as 2 here. 2 times 2 plus 1, 5. Answer. Yes, that's true, but we are saying that the concept of limits is not about substitution directly. Yeah, it's just a means of solving algebraically. But the actual picture is that the function goes close to 2. So you have to confirm this if the function exists from both hands. You check the limit as x goes to 2 from the left. You check from the right. Are they the same thing? Yes, the limit exists, and that is the limit. So here now, how do we solve? We'll go again and check the limits. The limit as x goes to 2 from the right of 2x plus 1. In this case, we are putting numbers close to 2 and greater than 2. That is from the right. So, which numbers do you think is like that? Numbers close to 2 and also bigger than 2. I can say 2.01, 2.001, 2.0001. Now, when you do your multiplication, when you check the function, you have 2 times this plus 1. 2 times 2.01, 4.02 plus 1, 5.02. When this goes in as x, we have 2 times 2.001, 4.002 plus 1, 5.002, and here should be 5.0002. Observe something. The more we try to go close to 2 from the right, as we are trying to go close to 2 from the right, we are confirming that the function is going close towards 5. So the right hand limit is also 5. Since the limit is equal, we can conclude that this function, the answer is equal to 5. Yeah. That's why most times in your exam, maybe OBJ, or even theory, you don't have to start using this table to solve the limits because it's time consuming. You can just go ahead and plug in your x as 2 in the function given to you to obtain 5. Like in this case, we will solve without using table. Let's solve. So let's solve this. Solution. How do we solve this? We simply take the limits. Taking the limits. This will be, we are going to plug s as 3. We know that s is approaching 3. How do we solve it quickly with algebra? We'll go ahead and plug s as 3. If you have something reasonable as an answer, that's the answer. Let's solve. So let's quickly put s as 3. That will be 3 plus 1. S is 3. All over 3 plus 2. And this is 4 over 5. That's the answer. When you go ahead and plug in your x as 3, what comes out is 4 over 5, which is reasonable. That's your answer. At times, when you take your inputs, when you take your limits, your answer may not be reasonable. Your answer may be indeterminate. Something you don't know the value of the answer. For instance, let's solve number 3. For number 3, when we take the limit, taking the limit, we are going to have this to be 2 going in as all the x. We'll have 2 squared minus 4 all over 2 minus 2. Now, 2 squared is 2 times itself, which is 4 minus 4. 4 minus 4 is 0. 0. 2 minus 2 is also 0. Now, what is 0 over 0? Undefined. Indeterminate. When you take a calculator and punch 0 over 0, you will see math error. This is nonsense. So we can't end up and say that nonsense is our answer. We have to evaluate further to get the actual answer. What do? We apply some algebraic process. We can factorize. Yes, let's factorize. Factorizing, we have it that the limit as x tends to 2 will give us x squared minus 4 is x squared minus 2 squared. Yes, 4 is 2 squared. 1 over x minus 2. And we'll call this difference of 2 squares. A square, difference of 2 squares. So we can also make this to be like this. Difference of 2 squares can be expressed as the product of the sum and difference. Yes. S plus 2, s minus 2. How we expand difference of 2 squares. If I give you n squared minus m squared to expand, what will you do? Say n plus m multiplied by n minus m. The concept of difference of 2 squares. That's it. So here, difference of 2 squares for this will give us this. All over x minus 2. At this point, this can cancel this. We're now left with s plus 2. When we now take our limits the second time, as s approaches 2, we plug s as 2. What happens? We have 2 plus 2, and that is equal to 4. We have solved it. So it's a good approach to substitute your limit directly. When you have something concise as a finite real value, that's your answer. But when you have 0 over 0 or indeterminate form, I will still show you some more forms of indeterminate. Something you cannot determine. Check through the app, you will see various forms of what things you cannot determine. In those cases, you find a means, a way of solving the limit to give you a real valued answer. Yes. Yes. So now we'll take more examples to learn how to take a limit approaching a real value. Let's take more examples.